Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Geometric optics, duality, and congestion in Sensornets. Here's Christos.
Thanks.
Oops.
Let's see now.
Good.
Okay, cool. So, always delighted to be here. Thanks for coming. So this is joint work with lots of people. So I'm standing on the shoulders of very tall people. So. So this is about Sensornets. By this I mean small devices that communicate by wireless, and as a result, they have very stringent limitations related to power. For example, this means that only devices that are close together can communicate. And this is, I think, a very interesting, very active area for research for theoreticians. The reason is, that there are manifold. First of all, theoreticians have been accused of being overly concerned with with resources. Okay. Whereas computers are becoming faster and nobody cares about memory and time anymore. But the point is that these people care, okay? Also there is no end to the scale of how big the sensors are going to be. The problems are new. They are quite a bit different from other networking problems. The community that does this research is very closely connected to the community that's doing internet research, and we have been hooked up with this community. And also it's a very young field with no idea fix and dogmas, and as a result, these people are open and are likely to be patient with theorems. Okay, so and hospitable to theoreticians. So. I'm going to talk about one particular problem, by far not the most important and central one. It has to do with routing. When Sensornets, ad hoc networks are called at some point also, their main characteristic is that they are ad hoc. Okay, so they are somebody sprinkles a few modes around, and then they're supposed to come up and run, and as a result, routing is yeah. So routing has to be done in a way in the absence of what we have all been used to, the internet protocol and IP addresses and so on. So what people have to do instead is very crude devices. Like, for example, using geographic coordinates as a surrogate for IP addresses, and doing something like what I call greedy routing, which is basically the main mode that I'm going to consider in this talk. And greedy routing simply says, look around you and give the packet to the person that you can talk to and is closest to the destination. Okay, that's what greedy routing means. And greedy routing is full of problems. Problem number one, it often gets stuck. In other words, you do this and suddenly you arrive at a place where there is no way to continue, okay, by the same algorithm. And I'm going to talk a little about that in the beginning. And the second problem, which is the main part of my talk, is that central nodes are overburdened. There is something called the busy center problem, okay, which means that if you are centrally located, chances are that you are going to do nothing else but passing packets around for other people, and as a result you are going to run out of battery more often than the people who are in the boonies. So let me tell you a little about the first problem, that the greedy algorithm gets stuck. For example, if you want to send a packet from here to there, it's going to get stuck there. And notice what happens here, that this person looks around, looks at the closest, at the one, at the node which is closest to the destination. It's this one. This one looks around and gives it to this one. Okay, so this doesn't go. And the reason, the culprit for that is what we call a lake, which is sort of, a non-convex convex can be bad also, but non-convex is death. Okay, so it's a non-convex phase. There is a simple idea for getting around this, what we call fake coordinates. So it's enough to convince this node that it's not here, but it's there, okay, for this problem to be fixed. Okay? And so, to put it otherwise, you want to take this graph. Incidentally, these graphs come from a new genre of random graphs called, I believe, geometric random graphs. Okay, and they are a very interesting sort of awfully complicated, frankly.
So what characterizes it?
So basically, they are the following kinds of graphs. You throw pennies on the plane, and you see which ones intersect. You draw an edge if they intersect. Okay, so that's so this gives you sort of, it turns out that almost all the theorems you know and love about Erdos-Renyi graphs hold for them, but have like 10 times more complicated proof. So it's sort of there is a book out by Penrose, not the physicist. Matthew Penrose, yes, right. Yeah. Okay, so a particular idea that we came with my collaborators a few years ago is the following. So the question is, how do you find these coordinates? Okay, and here is something that to many of you will be obvious and very familiar. Imagine, think of these. So look at this picture, at this problematic picture. The problem with this node here, or the position of this node, is that it's not in a natural equilibrium. I mean, if you imagine that the lines are rubber bands, okay, you don't expect the node to be there. Okay, so whereas if this picture is more consistent with the sort of the hypothesis that the lines are sort of rubber bands. So the idea is something that a lot of people in our community have used, most notably Lassi Lovas. Imagine that the links are sort of rubber bands whose energy is the square of the length, and these guys want to be short. You let all the internal nodes move around freely. And with experiments, my colleagues have shown that with the resulting fake coordinates, the greedy routing routes successfully, not 70% of the time as it used to, but 99% of the traffic. Okay, so it goes a long way towards. Still, you can get stuck, but it's now very. It's actually an interesting open problem. Sort of, can you prove that the probability of getting stuck is overwhelmingly small?
Are you doing these experiments with random points in the square?
Yes. Starting with random geometric graphs. Yeah.
How dense is it?
So you vary the density a lot. Yeah. There is a paper in Mobicom 3 years ago, that describes this experiment.
How does the node compute its coordinates? This looks like a global operation.
So it turns out that the equilibrium in this game, in this situation, is you want to be in the geometric average of your neighbors.
Like
So yes, you do it iteratively, right? I mean, and you stop. It makes no sense to go on after 10 iterations, it turns out. So, it very rapidly converges.
Wait, the measure of success is just that the message gets through?
Yes.
Then why does distance matter?
Distance matters because distance is what the algorithm uses, the natural algorithm uses. We know of no other, no better algorithm.
You care only about...
Yes, of course, yes, right, yeah. Yes, okay, yeah. Sure. Radomoku. So the tragedy with this research is that we were not able to prove anything about this. Okay, with a student, David Radajak, with Department of Quest, there must be a theorem here. Okay, so we'll try to find it. As I'm going to tell you, we identified a great conjecture. But so the question is, I give you a graph. Does it have a greedy embedding? A greedy embedding means the following. That you put the graph on the plane, and then it has the following property, that in the shortest path between any two nodes, the distance is always decreasing. Okay, the distance to the destination is always decreasing. That's what you want. Okay, so this is
the greedy path.
Sorry, in a path there is a path where the distance is always decreasing. Right? Yeah. So do all graphs, and the answer is no. If you look at this graph K24, no matter how you draw it on the plane, it's not going to have a greedy embedding, because to go from here to there or from here to there, you will have to back up. So not true. Not all graphs have a greedy embedding, but this graph has is not triply connected. So the question is, do all triply connected graphs have a greedy embedding? And the counterexample here is also easy. K319 turns out not to have a greedy embedding. Here's how you can see it, okay? That in a greedy embedding, so the node which is closest to you must be your neighbor, okay? There is no other way about it, okay? Because imagine that you want to talk to him, okay? What you are going to do. So in K319, one of the three nodes are going to be closest to 7 of the other guys, okay, by a pigeonhole, okay? And no node in the plane can be closest to 7 nodes, okay? So that's sort of the idea. That doesn't work. So how about then the next? How about every 3 connected planar graphs, or a class that we know and love? Do they have a greedy embedding? And yeah, we strongly believe that they do. Okay, that's a neat conjecture. Seems to be not very easy. So we have worked on it for a long time. We have discussed it with people who should know, and seems to require sort of. It's true for triangulations. If you restrict triangulation, it holds. That's Alexandra Kola's result. Yeah.
Could you repeat the definition of a greedy embedding?
Greedy embedding means the following: that the greedy algorithm works. Okay, it means that it means the following: for any 2 nodes, if I choose if this guy chooses his neighbor which is closest to the destination, and so on, it will never get stuck. Make sense?
Is sort of the congested center?
In a minute. Okay. Yeah. So this is sort of this is in some sense I wanted to tell you something about this problem also, because it's I'm switching gears immediately. So it's true for triangulations. With David Ratajak, we came out. It's also easy to see. So wrote a paper about this, that it's true in 3 dimensions. So if you want to embed it in 3 dimensions, you can do it. Here is how you prove it. Very easy. Every triply connected planar graph is basically a polytope. Okay, and so you see it as a polytope, and then you can route by simplex. Okay, it's very easy. So it essentially holds for 3 dimensions, even though you have to change the metric. It's not a natural metric. And Bobby Kleinberg came up with something called hyperbolic embedding. Many of you immediately know what it is. Sort of, you sort of embed the graph in the hyperbolic plane, and this works, even though sort of it's not what we had in mind. So, as I said, I'm wrapping up this part of the talk. What we came up, sort of, we looked hard and we came up with a neat conjecture, I think. Okay, so incidentally, a conjecture that could be easier is the following: that every triply connected graph has a subgraph that can be embedded. Okay. Yeah.
But your graph with intersection of disks is not a planar graph. It has a lot of little.
Yes, that's true. That's true. Yes. Right. So why am I interested in planar graphs? Okay. Okay. Because okay, it's sort of it's a long argument. I mean, it's you can find a subgraph, a planar, unless you're so if you're non-planar, okay, and the reason for your non-planarity is K5, then you can find a sub. So you have no K33s, then you can find a planar subgraph which is also triple connected. Okay, and therefore you can in your graph also you can route by greedy routing. If you have a K33, we don't know. Okay, so that's the short. Okay, so now I'm switching gears and I'm going to the second problem, which is completely different. So you can start afresh. If you are lost. So in large networks, greedy routing, if the network is dense and you have two nodes and they and sort of their greedy routing goes like this, then it's essentially sort of straight line routing. Okay, so you can assume that it's sort of like a straight line. Okay, it wiggles, but it's really good if the network is dense enough. Okay. So, suppose that you have a circular region and uniform distribution. Incidentally, this title is the part that my practical colleagues hate. Okay, because especially the uniform distribution. Okay, in the sense that so I'm assuming the following experiment. Okay, conduct the following experiment. Pick a point at random, uniformly at random from the disk. Pick another point. Draw the straight line. Okay. So this is not a very attractive model because in Sensornets it's known that the distribution of origins and destination is not uniform. Okay. Even though you may believe that the sensors are sprinkled in a disk. Still, sort of, you don't have a uniform, but suppose it is. I mean, in some sense, the clean problem is this, okay? So, intuitively, the routing, which now we decide it's straight line routing, affects congestion. So, in other words, these two people, in order to communicate, they must bother everybody on their path, okay? And depending on where you are going to be more or less bothered, okay? And the problem is that if you are at the place where you are bothered maximally, and you can all guess where this place is going to be, then you're going to run out of battery earlier, okay? So the whole operation is going to sort of so that's sort of the idea. That's the concern, that the maximum congestion can be very large. So let's see what's the congestion you know, it's a symmetric problem. So let's see what's the congestion at distance r from the center. And so here is some neat Euclidean geometry. Intuitively, the congestion at this point caused by origins and destination of this line is sort of like the product of these lengths, right? And the product of these lengths is the same. Now, if you draw this perpendicular line, is the same as c squared, okay? Because these two triangles are similar, okay? I learned this in 10th grade, okay? So, and therefore, it would appear that the congestion at r is something like 1 minus r squared, okay? Not quite, not exactly. Yeah, so what Lassie caught is this, that these are not exactly lines, but they are wedges, okay? Okay? So this disrupts this calculation, and the final result, sort of, you know, which, you know, I haven't had to, you know, it's actually a few pages of calculation, is you multiply by this correction, okay, by this integral. And this actually drops the congestion by something like 8% of the average. So the final result is this, the congestion at R, and if you wish, modulo my sort of, you know, my shaky hand, sort of, you know, it's a curve like that. Okay? And the maximum is 1, so at the center, as you all suspected, so, you know, it's maximum at the center. And the average is 0.46, okay? Without the correction, the average would be 0.5. Okay? So that's, we know that. Now, so 0.46 is the average of the straight line routing. If you think about it, straight line routing, for any two origins and destination, for every pair, does the smallest possible disruption. So it has the smallest average, okay? It's easy to believe this, okay? Because it goes by straight line. How else can you sort of, you know, how else can you minimize the average? So it's less than or equal to the average of any routing scheme. So if you go in roundabout ways, you are liable to spend more on the average. So, and since the average of anything is less than the max, it's less than the max of any routing scheme, okay? So we have a lower bound, okay? So we know that that 1 is sort of, you know, what straight line does, and we know that you can not go below 0.46, okay? So if you are not interested in constants, okay, that's, you know, you can leave, okay? So the point is, or, you know, where in between can you, what can you do in between? So what are our results? Okay, so basically what you want is to find routes, like probably some roundabout ways, to minimize congestion, so that the maximum congestion is somewhere here, okay? And the question is where it is. And the answer is, frankly, we don't know, okay? But we don't know in a couple of interesting ways, okay? So,
but you don't know where are you from the center. What is your distance to the center? Or you assume you know this information?
Yes, you know this information. Why does it?
Node knows its distance to the center.
So listen, I mean, at this point, that's actually you are breaking up a very interesting point. I mean, right now, what I'm saying is, okay, I'm designing sort of, you know, this routing scheme, okay? I'm ordering this node and this node to communicate via this path. I'm not telling you anything else, okay? I'm drawing curves on the disk, nothing else, okay? Now, how I'm going to implement this is a different way, okay? But definitely, minimally, the nodes are aware of their location, okay? So in any event, the question is how do you do this? And here is what sort of in a snapshot our result. We have a scheme, sort of, you know, which experimentally is like that. We have, and then we have the min-max. Okay, we show how to show a way to find the min-max, which are actually up to the exact optimum which is somewhere there, but you don't know exactly where. Okay, so experimentally speaking, this is quite close to the 0.46, which is the absolute minimum. So this looks like a neat algorithm. So I'm going to explain. So the question is, how do you do this? How, what are ways of going from here to there in order to minimize, to avoid the center, so to speak, okay? One way, imagine that you want to go from a suburb to a shopping mall somewhere in the city, right? So what do you usually do? So, you drive around in the periphery somewhere, then you jump to the right radius, and then you go here. I mean, so this is one of our first, so you go drive around, jump to the center, and then finish by circular arc, and you optimize where to jump, okay? So we did this, we optimized it, we did it right, and it's not a good idea, okay? So it doesn't work. It gets you down to 0.85 or something, so it's not. So our next, actually, I guess, influenced by our previous work, we want to use fake coordinates. In other words, this node is at R, okay? We want to convince it's somewhere else, okay? And then, if we convince every node that they're somewhere else, if we have used fake coordinates, maybe the routes are going to be clever enough that the congestion is minimized. And we tried several things, and this doesn't work either. Okay. So here is another idea. I know nobody wants to think about air travel today, but you'll have to for a while. Okay. So here is one idea. You look at this. You have this disk. Okay. You have these 2 points in the disk. You look at them. You look at these 2 points, and you imagine that you are sort of way above the North Pole. Okay. You look at these 2 points, and maybe these 2 points are just Tokyo and Rabat. Okay. And you are thinking, suppose that an airline wants to fly from Tokyo to Rabat. How would they do it? All right? And they will do it by geodesic, okay? So they're going to go this way. Okay, so you do this for every point. You make them believe that they are on the surface of a hemisphere, and then you make them follow geodesics. Okay? And in fact, you can optimize the z-scale because nobody tells that it has to be exactly a sphere, right? I mean, you can do many things. We did this. It works, but not as well. Another projection works better. So imagine that this is the disk we start with. We think of a sphere that has it as its ring, as its Saturn ring, and then we project this way. And this is what we call curve ball routing. In other words, in this projection, now the points route to each other on geodesics. Okay, which is a very simple operation to do. They know where they are on the disk. They figure out where they are on the sphere. They figure out how to follow geodesics.
Center of the disk, where will you project on the sphere? You're inside the sphere.
Near the center of the disk, it's
inside the sphere. The disk intersects the sphere, or no?
Yes, that's actually right, isn't it? Sorry, I believe that you go to the southern hemisphere and then up. Okay, that's why over here you have yeah. So I have to look it up, but I believe that you go that you go to the southern hemisphere. Okay. Yeah. And there are several things you can optimize here. and sort of the ratio of the radii, the z-scale, and so on. And it turns out that this gives you both experimentally, by simulation and by actual experiments, a reasonably small congestion. Sorry?
I was wondering if you could tell us why it turns up like that, and give us some reason why.
If I remember correctly, what happens is that if you are in the periphery of the disk, then essentially you are projected to the North Pole or very close to the North Pole. Okay, and then the density becomes very high. And there should be ways to get around that, because this is sort of, Lucian Popa, who is sort of, doing this work, has tried a lot of things and sort of, and is satisfied that he can't make it work better than this. In any event, what I want to tell you is that there is a way that you can think about the optimum. Okay, you can think about the actual min-max, and the optimum, you can think of it as what you want to do is you want to optimize an infinite dimensional linear program. So if you have 2 points, you can consider all possible paths. And the optimum routing will choose one of them, of course. And then you subdivide the disk into many rings, infinitesimally small rings. And every path burdens each ring by some amount of congestion. Basically, it's the angle with which it cuts the ring. Therefore, you have a linear program. You want to minimize T, where T is sort of, the maximum congestion, so that every pair of nodes chooses perhaps how do you call it, a lottery of paths. Every ring is burdened less than this absolute maximum that you want to minimize.
So you're allowed to split the traffic.
You are
to split the traffic between 2 points?
Yeah, you don't care. Yeah. Okay. But the theorem will say that what will happen at optimality. Okay, that there is. Okay. And it turns out that you can write a dual. You realize, it's impractical even to think about this linear program. Okay, not let alone sort of write it or implement it. But the dual is this, and the dual has essentially a physical significance. That these dual variables beta are sort of the resistance of the material at every ring. Okay, they're sort of the inverse speed of light at every ring. And this means the following, that
Index of refraction, basically.
right, the index of refraction. Yeah. So basically, recalling Snell's law now, sort of my title comes together. The theorem says the following, that there is a function beta mapping sort of every distance from the center to the negative reals, such that the optimum routing scheme consists of light paths where the speed of light at radius r is 1 minus beta r. Okay? And whenever you have a non-infinite speed of light, the resulting congestion at the radius r is maximum. So basically you expect everything to be at maximum congestion, okay? Except for singularities, which they don't come up, it turns out. So in a way, the optimum thing to do is imagine that the disk consists of a transparent material of varying index of refraction, And therefore, so, and then the paths are shortest, are light paths from between points. Okay. As a matter of fact, believe it or not, you can have a primal dual algorithm, and notice that the quotes are on primal dual, not an algorithm. It's actually an algorithm, okay? So you subdivide the disk into finitely many rings, okay? So you discretize the problem. You start with any sets of speeds of light, and you calculate the shortest paths. You compute the congestion, and then you decrease the speed of light where congestion is high, you increase it when it's low, and then you repeat. So this is actually something that you can run, and it is the primal dual algorithm for the, discretized primal dual algorithm for the infinite problem. And it turns out that the optimum seems to be this, okay, a cubic curve like that. Okay, so we can only, calculate it with as much accuracy as we can, and until accuracy does not improve the result, and this is what we get, okay? And I'm sure that when we write this paper, we'll have some theorems that say sort of, how the accuracy relates to, that we use relates to the accuracy of the problem, of the result. But, and indeed, if you have a speed of light like that, the congestion is everywhere the same, okay, and it's very low.
So you make the speed of light faster in the center where things are very...
Actually, you slower, because you want to discourage light.
You make the index of refraction higher.
Right. You want to discourage light to go through there. Yeah. Yeah. Or you can see it this way, the following way. Okay. I mean, imagine that this is like you are trying sort of to legislate a city like London, where sort of you have to pay to go into the center. Okay, to go into the central ring. Suppose that you are trying to find the optimum charging scheme. Okay. Well, this is the optimal charging scheme in some sense, right? I mean, it says that if you want to go to the center, you have to pay, or pass through the center, you have to pay through the nose, okay? But it gets smaller and smaller. So I mean, I guess Athens is also like that. I mean, so all these mayors have imposed step functions, okay, which is stupid if you think about it, right? Because it means that there is congestion in the right. I mean, what a step function in this means that in the congestion there is going to be a jump at the boundary of the right. So if you have a continuous function like this.
How do you enforce this?
well, excellent question. Yeah. So I got
They got the factor of 2 right. In Athens, right.
Yeah. So you're absolutely right. Yes.
Well, we can have like this continue. Now they're doing it electronically in a lot of places.
Right. So
you could just say the highest point at which you've entered is the amount that you're charging.
So it's not beyond sort of credibility that soon sort of all the cars will be equipped with some kind of frankly sort of it will make a lot of sense. It will probably reduce pollution and travel a lot. Sort of if you cost to society that much, please pay. Or we'll take your car. Yes, hello. Yeah.
So you started out by saying the practical people didn't like the uniform
Yeah.
assumption. Do you actually need the uniform assumption
No.
Start out with
Could start out with any distribution. So you can do the same thing. Okay. Right. Exactly. I mean, so you are right. I mean, so you're absolutely right. Actually, I mean, we are hoping to have a closed form. We don't have a closed form, okay? So if we don't have a closed form, why do we need the need mathematics, right? I mean, so we could start with any distribution. You're right, yeah. And we will get another kernel like this. Yeah, good point. Yeah, yeah.
Could you have a routing algorithm that adapts to the congestion, like look at only your neighbors who are not maximally congested and try to route through those only?
So the reason this doesn't work is the following, okay? I mean, so something like that would not work. Here is why. because you don't want to look at locally at the congestion. You want to go, so the problem is that you have to look globally at the congestion. Okay? Suppose that it looks good to go this way, but further down the road, okay, there is a lot of congestion. Okay? So you really have to find the Dijkstra shortest path. Okay?
But the dual will be a metric, right? So the question is whether that metric can give a code.
Precisely. Yeah. So this takes me to my open problems. So yeah.
Just one more question. Suppose like you have a city like Athens that's got these obstacles, like there's some water here and there's a mountain there. Again, all of this would just work, right?
So you can exactly obstacles and so on. Yes, yes. You have I see no reason why the precise same linear program and the precise same optimization would not work there.
But here you kind of, like this, in terms of the number of variables, you just
Yeah.
calculate this from the center.
So then it would not. It would be the speed of light would be a function of the point you are, not just the distance. I mean, the symmetry helps a lot, sort of, in the formulation. But
Actually, the solution tends to be a single path, or it's because solving the linear programming not necessarily it's not necessarily an integer programming.
yes, it definitely results in a single path.
Well,
Yes, because single path is
if you look at arbitrary small neighborhood, you already have a continuum number of paths, so you can just sort of redistribute it. I mean,
No, but if
all
you
of them want to go like this, then you can let one go.
No, but if you use this curve, then all of them will follow the same path. Actually, if you assume this, then all of them will follow the same path.
Unless there are several shortest paths.
So if you want to go between two antipodal points, there are two paths. Okay, one goes up, the other goes down. So you can't have two shortest paths. Yeah. So in this case, you could split, and it would make a little difference. Yeah. Good. So we were hoping all along that we'll find a closed form for the optimum, but this didn't come along. So that's an interesting problem. A more interesting problem is the following. We haven't been able to find, so basically, how do the question is, how do you implement this? Okay, I mean, we know how to implement the curveball routing, the heuristic that I showed you before that works okay. You implement it by letting everybody imagine that they are on the surface of the sphere, and then use that metric to route. This one we have no idea how to implement. Okay, it would require that, of course, you can have a routing table for every point. Okay, to know if you want to route there, you should send it in this angle. Okay, to have sort of a table, but it wouldn't. Basically, what you want is an easy local way to calculate.
Is that what Claire was asking? Or that was related to what you were asking about looking at neighbors. I mean, that was...
Right. But the point is you cannot. Okay, you cannot. Right. I mean, you have to do a global...
Even if you wait till you reach an equilibrium?
Hmm?
Even if you wait until you reach some equilibrium?
No, but the point is that so you are imagine you are in a graph, okay? You look at your neighbors. Which way should you go? No idea. This looks promising, but maybe Dijkstra will give you something else. You know what I'm saying? It's exactly the same problem. It's exactly the same problem. You have to look at everything between you and the destination in order to decide where to go. Okay? Now that we have sort of some kind of, we know the approximate form of the cost. Okay? We could hope to be able to have a simple formula, sort of, that says, all right, you should try to go in this angle, okay? But we haven't been able to do this, okay? And that's in some sense the practical open problem. Can you have a local way of computing where to start, which direction to start if you want to go anywhere on the disk?
One question. I mean, this has something to do with random walks, because proving convergence of random walks, you would prove that there's a multi-commodity flow. I mean, one way of proving would be to relate it to congestion and the multi-commodity flow. I mean, for instance,
Sure,
processing
of course,
layers.
of course. Yeah.
So I don't know whether that connection is worth looking at. For example, I mean, here's a local search algorithm which is very inefficient. You just do from this point you do a random walk, and condition on getting there, pick that path. Of course, this is going to take.
Right,
It's not going to do
Well, yes, I mean, so there is something else. I mean, we tried some, a more modest proposal along the same lines, which is like Bravner and Valiant. You pick another random point on the disk, you route there, and then from there you route by straight line. That doesn't work. Okay, that's
These will be shortest paths. These will be shortest paths. No?
You go by straight line. Yes, right.
No, I mean the optimum paths that you are constructing. Shortest paths with respect to some weighting of the.
They are shortest paths. Yes.
We weight with the reciprocals.
Right. Yes.
So it's like the fastest path if you were thinking of how light would travel through it, given the index of refraction. Fastest, right? Then it would be a fastest, shortest, whatever.
Yeah.
Fastest.
Yeah, they are shortest paths.
So you could compute the potential and just move in the.
It depends on the destination.
No, but it depends on the destination. So the question is that I'm here. I want to go there. The question is, I know that there's going to be some kind of curve. The question is, what is the tangent where I am? That's what you want to know.
We don't even know the
and
starting angle. After that,
you want, everybody will compute the tangent. Okay, but the point is, where is the tangent? And this is something that we don't know how to compute. You can, of course, tabulate it, but that's not a.
So is there a theorem then that there would be a refractive index function?
Yes,
So that-
yes,
so
yes,
that
yes,
the
yes,
shortest
yeah,
part
right,
of
yes,
light
yes,
is the right
yes,
way
yes,
to
yes.
go.
That, essentially, that's our main result. Yeah, that there is a yeah.
This is a lot like first passage percolation. I don't know if you know that there are times along every edge, and so how long it takes to end.
Right.
And you're supposed to find the shortest time.
Yeah.
So. And the time would be related to the congestion.
Yes, right.
So if you know the dual value, you know the refractions, right?
Right.
So the primal dual has a local compute, can
Yeah.
be implemented locally.
Yes.
So one way is to solve the primal dual.
No, it cannot be. It still cannot be implemented locally. This gives you the dual variable,
Right.
and at any point. Okay, but then you have to, solving the restricted primal, the restricted dual. The restricted dual is finding shortest paths.
Right. So suppose you know all the dual, right? All the dual variables.
Right, but it's the same. It's exactly the same as finding shortest paths. The point of shortest paths is that it's a global operation. Okay, finding shortest paths in a metric is global. Okay, in other words, you cannot look at your neighborhood and say, yeah, probably it's this way, because you can't do it in graphs. Does that make sense?
Right. Yeah,
Okay.
but there is one message passing algorithm that computes the dual, right? Another one will do the compute the alter shortest path, so that if you get it from this direction, you pass it in the other.
Right. My problem with this is one of practicality. What you want is a way to locally compute where to start. Okay. So imagine the following: you have a huge graph, okay, that has arbitrary weights. Okay. You are at this node. Okay. It has many neighbors. You want to know where to go if you want to go there. You cannot decide locally. There is no local decision. Okay, you can tabulate. You can say if you want to go to these nodes, you start there. If you want to go to these nodes, you start there. If you want to go to these nodes, you start there. But tabulating is not, of course you can tabulate. I'm not saying it's a difficult problem. But it's not a reasonable thing to expect every node to have a huge table that tells it where to go. You want something very simple. that is computed locally. So
Yeah, but suppose you got the metric and then you embedded it in some dimension. You got some coordinates.
Yes.
Right. So that.
It's not. You cannot compute it. In the okay. So here's the difference. In our first, in the heuristic, you have a place where you know the geodesics. Okay, the geodesics are easy to compute. They are large circles. Okay. Here you don't know the geodesics. You don't know how to start the geodesics.
Local rule for the geodesics, some other equation.
Yeah,
you know how to start, then.
If you know how to start, you are done.
Then you are done because
If you know, no. So
you miss it from the left or from the right.
you can definitely do that. Okay, but the point is that it takes it takes non-local computation to do this. You have to shoot and then see where it went, and then shoot and see where it went. So I'm not saying that it cannot be done. I'm saying it cannot be done in a local way, by a very simple rule, as for example was the case with the northern hemisphere thing, okay, where you know exactly where to go next.
Well, you know that because you know the metric there, and therefore computing the geodesics, you actually do have non-local information, namely that the metric is uniform. Here, you always need the information about the metric to compute the geodesics.
So let me put it this way. It's an analytical problem. It's an analytical problem. So it's an integration that we don't know how to do. Okay, we know this function, and it's an analytical problem that we have no idea how to do or approximate it. So it is an analytical problem. In principle, we should be able to do it.
Yeah.
Okay, but
this is always true that to calculate the geodesics in a given metric, you need
global.
You need global information on the metric, and it's just if you know the metric's uniform, you have global information. But this is something that physicists will do all the time. They will calculate the geodesics in a non-trivial metric, and
well, yes, okay, so we're not physicists enough, I guess. Yes.
Well, I don't know. I'm just saying that it's not. Are you saying it's a computationally difficult problem? What are you saying about the?
What I'm saying. So I know how to formulate it as a sort of integral equation, and I don't know how to solve it, and neither does Mathematica.
analytic.
Yeah, that's right. Yeah.
It's just like moving between 5 planets. You can't solve it analytically.
Yeah.
Even though you have a local force field to it.
Is there what about the opposite question? Is there a distribution where you have more points in the
Where straight line.
Where the straight line is the optimal solution?
That would be great. That would be great if we've had that. I've been thinking about exactly this. Here is why. Because then you would have a way of inverting the problem and making everybody believe that they are there, and then and then shoot in straight line. But we haven't found it. There should be. Yes.
It feels a lot like fluid mechanics, and they wouldn't be just satisfied with a steady state solution. They'd also want to know about things like turbulence.
That's right. I see.
And that's where the obstacles and stuff become.
Yes, you are right. Yes. So here we are very smooth, and everything works fine. But you are right. In my experience, the phenomenon that I tried to allude to before, that when you have a sort of a steep increase in the price for a region, then in the boundary of this region there is a lot of there is a discontinuity in the congestion. Okay, so that's this is sort of like also recalls fluid mechanics.
But this is more like Maxwell than like the Navier-Stokes equation, and so I'm not sure where the is there like a viscosity term here or something? It doesn't seem to me there necessarily is. I don't know.